Center for the Ethiopian Educational Information and Communication Technology presents Educational Satellite Television Programs.
Hello, teacher. Hello, students. Welcome to today's lesson on the buffer solution. In our last lesson, we discussed the common ion effect. We learned that this effect occurs when two substances which both ionize to produce the same common ion are involved in chemical equilibrium. After reviewing Le Chatelier's principle, we learned how it applies to the common ion effect. We also looked at some effects of common ions and the process they undergo. You have already spent some time learning about buffer action. In today's lesson, we will demonstrate the buffer action that takes place between acetic acid and sodium acetate. We will describe the changes that take place during this reaction. We will also discuss an experiment which involves the process of measuring the pH of a buffered solution using a digital pH meter. Students, let us begin with an activity. To review what you have learned so far, explain what a buffer solution is and why buffer systems are so important.
Students, let's get ready. Begin. Time's up! Let's get back to our lesson.
Hello, everyone. I am sure you had no trouble with this activity. A buffer solution is a solution that resists changes in pH from the addition of a limited amount of an acid or a base. Buffer systems are important to both chemical and biological systems. The pH in the human body, for example, varies greatly from one fluid to another. The pH of blood is approximately 7.4, while the gastric juice in our stomachs has a pH of about 1.5. These individual pH levels are very important for maintaining proper enzyme function and the balance of osmotic pressure. In most cases, buffers maintain these pH levels. Let us continue by demonstrating the buffer action between acetic acid and sodium acetate. In order to do this, we will calculate the pH of a buffer system that contains 1.0 moles of acetic acid and 1.0 moles of sodium acetate. We can use the method that we have previously used to calculate a solution that contains common ions. I am sure that you recall doing this in our last lesson. We began by making a list, like the one you see here, of the initial molarity. The change in molarity and the equilibrium molarity of the different components of the reaction. The acid dissociation constant is equal to the equilibrium concentration of hydronium ion times that of acetate ion divided by equilibrium concentration of acetic acid, which equals X times 1.0 plus X divided by 1.0 minus X. This equals 1.8 times 10 to the power of negative 5. If we assume that 1.0 plus X is approximately equal to 1.0 and 1.0 minus X is approximately equal to 1.0, then we come to this conclusion. 1.8 times 10 to the power of negative 5 is equal to X times 1.0 plus X divided by 1.0 minus X. This can be simplified to X times 1.0 over 1.0. X equals hydronium concentration, which is equal to 1.8 times 10 to the power of negative 5 moles per liter. Therefore, the pH is equal to negative log of 1.8 times 10 to the power of negative 5. Our final answer is a pH of 4.74. Students, let us now discuss an experiment with the objective to investigate the buffer action of acetic acid and sodium acetate. To begin, 5 milliliters of 0.10 moles per liter of sodium acetate is mixed with 5 milliliters of 0.10 moles per liter of acetic acid in a 200 milliliter test tube. When you have a weak acid and you add the salt of that weak acid, you have a buffered solution. Into a second test tube, 5 milliliters of 0.10 moles per liter of acetic acid are added. 100 milliliters of distilled or deionized water are then added to a third test tube. 5 drops of universal indicator are added to each test tube, and the pH is estimated. The initial pH of the buffered solution is 4.8. The initial pH of acetic acid is about 2.4, and the initial pH of distilled water, assuming it is pure, is about 7. If universal indicator is not available, 2 drops of methyl orange indicator can be used. A digital pH meter would also work. The buffer changes to a yellowish orange color when the sodium hydroxide is added, which indicates that it is an acidic solution. Its pH remains at about 4.8. The distilled water changes to a purple color, which indicates that it is basic. Its pH changes to about 9. The test tube that contains acetic acid obviously turns red, indicating that it is an acid. Its pH changes to about 4. Next, 5 milliliters of 0.010 moles per liter of sodium hydroxide are added to each test tube. The pH is estimated again at this point, and any changes are recorded. Upon adding sodium hydroxide to each test tube, it can be observed that the tube containing the water remains basic at a pH of about 9. The tube containing the buffer changes only slightly, altering to a pH of about 4.7 and remaining neutral. However, the tube containing only the acetic acid begins to change color. As more sodium hydroxide is added, it turns basic and then eventually acidic at a pH of about 4. Students, please split into groups of 3 or 4. In your groups, please discuss what we can learn from this experiment in terms of the behaviors of buffered and unbuffered solutions. Write down the points that you discuss.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Hello again, students. I am curious what points you discussed in your groups. The experiment taught us that buffered solutions can be prepared by adding the salt of a weak acid to a solution of the same weak acid. The experiment showed us that when a small amount of weak base is added, the pH of the buffer solution will change only slightly, whereas the pH of the unbuffered solution will be more affected. Students, it is also important to note that buffered solutions react similarly when a small amount of weak acid is added. Today, we learned about buffer solutions. We worked through a problem involving the buffer action between acetic acid and sodium acetate. And we also looked at an experiment. This brings us to the end of our lesson for today. Until next time, thank you, teacher. Thank you, students.